This is the second statement for De Morgan's law under the topic on basic set theory. So we state here that if we have here the complement of the intersection of sets S and T, whatever they may be, is just equal to the union of the complement of S and the complement of T. Now, we cannot use here certain specific sets or elements of a set, or specifically for set S and set T, because set S and set T can be any type of set. It could be a finite set, infinite set, or it could be the empty set itself. But we can assume a representation or a sample element. We're going to allow it to be an element of our left-hand side and show that it's also an element of the right-hand side. As mentioned, this is the second video for De Morgan's law, because the previous video, the first property of De Morgan's law, talks about the union here and intersection here. So we're going to show that from here, it's equal to that. Now let us try to assume a certain element x, which is an element of our left-hand side, and we need to show that if it's an element of a left-hand side, it's also an element of the right-hand side. And since x is arbitrary, any element that can be represented by x could also be true for all. So let us try that x is an element of the complement of the intersection. If this is the case, if x is an element of a complement, that would mean x is not an element of the intersection. Because if we talk about complement, it is actually disjoint with its the original form of expressions of a set. Okay, so that would mean if x is an element of complement, it should be the element of this expression, or vice versa. If x is an element of this, then it's an element of the complement, because they are actually disjoint expressions. With this now, what can we say about x being on S and T? If x is not an element of the intersection, okay, so it's not, we talk about intersection, it's the common to both. So if we have the intersection of S and T, all elements that can be found to that are elements that can be found in both sets S and T. And since x is not an element of the intersection, this would mean that x is not an element of S, or x is not an element of T. Because if it is an element of S and T, that would mean that it's an element of the intersection. But since it's not an element of an intersection, we can have this statement. We use the concept of or here because it could go one direction. Even if it's only this one here and x is element of T, it can not be an element of the intersection, because for it to be an element of the intersection, it should be found on both sides. Now, what can we say about these two? If x is not an element of S, what does this imply as x being on S? This would mean that x is an element of the complement of S. As mentioned, they are disjoint sets, and if one object is an element of the other, it should not be an element of the other, or vice versa. This is also true that if x is not an element of T, this implies that x is an element of the complement of T. Okay? So these are just the interpretation of that. Now with this two, and the idea of or being the keyword for union, we can now say that if it's an element of the complement of S, and it's also the element of complement of T, we can deduce that E is an element of the union of both complements. Okay? Because if it's an element of complement of S, it's also an element of the union. If it's just an element of this, it should also be an element of union. If it's an element of both, much more, it's an element of the union. So with this now, we can now say that from here, if x is an element of the complement of the intersection of S and T, then x is an element of the union of the individual complements for S and T. This shows this second De Morgan's law is true. This is a part of the series on properties, laws, and theorems. Please subscribe now.